Okay, again, my name's Sal Stangaroni from Temperature Equipment Corporation. I'm in the controls department, and today we're going to be discussing proper applications and sequences for constant volume pressure dependent zoning, or more simply, VVT design and control. So let's get started. If you guys have questions, feel free to type them in the question box. I will get to them probably at the end unless I see them while we're going, and if they're quick, I'll try to give them a shot. But definitely feel free to ask anything you got. So let's get started. First, we're going to talk about a little bit of history and VAV systems. Not exactly the topic, but a very related topic. So VAV systems began in the 60s and 70s. The point was to save energy, improve comfort, control buildings that were a little bit more diverse, multiple zones. And the purpose of VAV, which I want to stress today with the difference between VAV and VVT, is VAV systems are when there is a cooling load all year round. Cooling is needed 364 days a year. That is a huge difference between VAV and VVT here. So just general sequence of VAV is you have one air source, and whenever that air source goes into occupied mode, it initially goes into morning warm-up mode, where it blasts heat and all of the zone dampers go to fully open position. Now it does this to get the space temperature back up to a reasonable set point, which would be your return air set point, or sometimes it's called the occupied heating set point. And once this return air temperature is reached, it switches over to cooling mode, and it maintains a discharge air set point for the rest of the occupied period. Again, it does not go back into heating mode other than the morning warm-up time, because a VAV application requires cooling all year round. So your air handler discharges, say, 55-degree air for the rest of the time, and each of the zones will modulate their damper based on that 55-degree air coming in. And again, no heat the remainder of the day. Where VVT comes into play is this application for smaller type buildings. Smaller buildings with smaller loads, you have units that don't have refrigerant capacity control, or in the guide vanes, more complicated control that's required for VAV applications usually isn't available for smaller tonnage units. So we needed to come up with something that could be used for just packaged rooftop units or smaller air handlers. Another part of VAV that was actually a little bit more expensive and not required for small buildings is you're actually reading CFMs and pressures at each zone locally. For smaller 5-zone systems, that's not necessarily required. You just want to get the different zones under their own control, and you don't need to know how much CFM is going into each. And then the big thing with smaller buildings was that there is not a cooling load required all year round. So because of that, we came up with VVT, which stands for Variable Volume and Temperature. There are a lot of different names for VVT. VVT was a trademark name by Carrier, but it's becoming more accepted throughout HVAC. But we're going to go over a few of the different names that were out there that would just reference any type of VVT system. So we have constant volume zoning. And when it says constant volume, it's referring to the air source or rooftop, not the actual zones. The zones do modulate or vary their volume, but the rooftop is providing one constant volume of CFM the whole time. There's also pressure-dependent zoning, where this is referring to the zones are working off of the pressure of the system. They're not trying to maintain their own pressure or own CFM. We have auto changeover VAV. And the big difference between regular VAV and this is you can actually switch from heating to cooling mode, which is what the auto changeover refers to here. We also have bypass VAV. This is because VVT systems have a bypass damper. When you have a constant volume of air serving zones and the zones are closing, that extra air needs to go somewhere. And because of that, you have a bypass damper that bypasses the air so that you don't explode ductwork. There's also shutoff VAV. I've never really heard of this one, but just if you hear it, it is for VVT. and then variable volume and temperatures, VVT. You also may hear VVT systems referred to as Parker system. That is because Parker was the developer of VVT, and 20, 30 years ago when these came out, a lot of the times they're referred to as Parker systems. So just for your reference, a little bit more on variable volume and temperature, why it's called that. It's called variable volume because each of the zones is varying the volume of air going to each zone. It's also called variable temperature because you're actually varying the temperature from the air source. That's the big difference between VAV. With VAV, you're only doing cooling mode, but with VVT, you can also do heating mode. So we're just going to go over some general guidelines for a VVT system and when you need it. If you have an air source or a rooftop unit where you have multiple zones, this would be a perfect application. Again, you have different size zones. Generally, we refer to smallest size, probably 1/4 of a ton to up to around 2.5 tons. The correlating CFMs for those are 100 to 1,000 CFM per zone. Typically, you don't really want to go over 15 zones. I mean, under 3 zones is maybe you just have one rooftop unit. You probably don't need zoning. But for over 15 zones, generally speaking, you have a requirement for cooling all the time because it is a big enough building for that. That being said, if you have a customer who wants to zone every single office individually, you could have more than 15 zones, and they could all be 1/4 ton zones, and you could have a 5-ton air handler on there or something, but with, I don't know, 30 zones. But that being said, you don't usually run into it, so we kind of say 3 to 15 is a general guideline. 3 to 25 tons per system, per VVT system as a general guideline. I like to say don't go above 20. Usually above 20 tons, you have a cooling all the time load, and you can switch to VAV. You have some sort of internal zone that requires cooling all the time. So, and then another one, buildings up to 40,000 square feet, just a general guideline. Here is a conceptual layout of a VVT system. Pretty simple. You've got a rooftop unit, a bypass damper, it's right here, and then your 4 zones of control. Just going to go into a little bit of how the general sequence and system is supposed to work here. To start off, each of the zones has its own space temperature sensor. That's these little white boxes here, and these zones are talking to the controllers for each of these zone dampers. Now, how the rooftop unit reacts to these temperatures is based on the set points of all the temperatures. All of the zones have their own set points, and they each have their own space temperature sensors. So if you look at this case, it looks like 2 of the zones are calling for cooling, one's calling for heating, and then one is in vent mode. So because there are 2 zones calling for cooling, the rooftop unit would actually be in cooling mode. Because of the vote between the zones, there's more call for cooling. The rooftop unit goes into its cooling mode. Now, it looks like this zone number 1 over here is probably closer to its cooling set point than zone 3 because the damper is starting to close off. So it's starting to satisfy and the damper is starting to close, whereas zone 3 is fully open. It needs that cooling air. And then if you look at zone 4 is at its minimum position because it doesn't need any of that cooling air. It just wants ventilation air here, so it's just going to go to its minimum position. And then normally this zone 2, is requiring heat. Normally it would go to fully closed, but it looks like there's a little bit of supplemental reheat in this zone. And because of that, you need to maintain a minimum airflow over that supplemental heat coil in order to prevent it from burning out and to get proper dispersion of the air, so it's set at its minimum position. So this is actually getting 55-degree air coming into it, but it's reheating it and providing heat to the space. And then you can see because some of our zones are close to closed, the static pressure in the duct would be increasing, so our bypass damper is actually open a little bit, not fully closed and bypassing air. This is into a return plenum. We're going to talk about bypass setup a little bit later, but ceiling plenums are pretty ideal for bypass dampers because it allows for proper mixing of the air. So just a little general 4-zone system, pretty simple. We're going to get into more detail here coming up. First, we're just going to outline the basic steps for designing a VVT system. The first thing you should always do when you're designing any system is calculate the cooling and heating loads. Obviously, it doesn't always work that way. A lot of times you just get a model number of an existing unit and you just say, hey, I need 15 tons because that unit was 15 tons, but that is not the right way to do it. A lot of things were oversized previously. We always want to get to do the heating and cooling loads before we actually select equipment. So once you have your loads, you want to start going through your general equipment selection, what options you have, if you can do multiple rooftops, if you have to do one air handler, if you have to do unit vents, any type of options you can provide for the system you want to look at. And then through that, you kind of just decide on, hey, maybe I can do 2 different rooftop units with zoning, or maybe I can do 3. Once you have your general idea of what large equipment you're going to get, then we move into what zones we want to do in the system, where we want to have the control dampers. So we get to decide where our zones are. Now we need to calculate our loads and CFMs for each zone. Again, doesn't always happen. If you have an existing system, you'll see a damper size. You'll say, hey, use that, but we always want to design it if possible. Once we have our loads and CFMs for the zones, we want to pick our diffusers. Now that you have the CFMs, you know what diffusers you should use. A lot of people say oversize them by 25% for noise. I like to say use the normal size based on the CFM so you get adequate throw and dispersion into the space, but everyone has their own rules of thumb here, so probably won't hurt yourself by oversizing by 25%, but again, you don't want any dumping. You want proper dispersion of air. Once you have your diffusers, then you want to select your dampers themselves, the sizes and positions of them. You want to size your dampers for 900 to 1200 feet per minute at the peak CFM of the zone. So when that zone damper is full open, you want to be maintaining in between 900 to 1200 feet per minute just for noise. Okay, the next thing you look at would be your bypass system. We're going to talk a little bit more about how specifically to set up a bypass system and design it later, but this would be something that you would look at, what type of space you have available to set up the bypass. But it is very important to set up the bypass system properly for proper function of the VVT system. Now that you have your bypass damper set up, you have your zone set up, you want to look at positioning the thermostats. Thermostat position is very important. You obviously don't want it exposed to any outer walls or any sunlight, anything that generates heat or cold, simply because that will throw off the reading in that zone, and that can throw off the whole system. If you have one zone that's reading super high or super low, that's going to affect the control of the rooftop unit, and because of that, you're not going to get proper control in the system. So once you have your thermostat position set up, you want to size your ductwork, your main supply and return duct, you need to size for the CFM of the unit, and then each of your branches downstream of the zone controllers will be sized for the CFM of each zone, the peak CFM. Supplementary heaters are not always used, but they are a nice feature to have if you have the budget for it, and you would want to look at where to implement these after you have your ductwork sized. And then finally, you'd want to go into selecting what specific equipment you need. You would talk to your manufacturer, your rep, and say, hey, I need a 15-ton rooftop unit and 6 zones. And then if you talk to Carrier, we'd give you a 48 TC, something along those lines. And then you would go into your control system for the VVT and what type of wiring you need, all of that. Real quick, I want to show you something I ran into the other day on a VVT system that I worked with a contractor at. We had one zone that was reading super high all the time, and this zone was actually split into 2, and there were two zones in a similar room, and one was reading like 68 degrees and the other was reading 75, and we found out that this zone sensor, if you can see it right here underneath the clock, was located right above a printer, and that printer is generating heat all day, throwing off my whole system, so I was calling for cooling when I didn't need cooling. So temperature sensor or T-stat location is very important for these VVT systems to work properly. Here's another conceptual layout of a VVT system. We have 2 air sources. We have AC1 up here and then AC2. AC2 serving the south side of the building, and then AC1 has the rest. As you can see, AC1, we have 5 zones off of here. And you can see these little red boxes are for supplementary heat. The reason we have supplementary heat on this system is because we have an east and west exposure. During the morning, obviously, the sun rises on the southeast and then sets on the southwest. In the morning, if you have a high heat load from the sun on this east exposure, you're going to put this unit into cooling mode. The problem is you're not going to have any heat exposure on the west side during the morning, so you're going to require heating because you have outdoor windows probably that are affecting the zone, cooling it off, or heating it up, cooling it off. So because of that, you would want a supplementary heater so that when the unit is discharging 55-degree air to these zones for cooling, you could reheat that air and provide either ventilation air or heating air depending on what this zone requires, and then vice versa for the afternoon when the sun is on the west side. And then because it's the same thing happens on the bottom zone because of the sun exposure, you got your east and your west, but you always want to have your south zone separate from the rest of the system because your south zone is always going to be exposed to sunlight, and because of that, you're always going to have, generally going to have a cooling load or cooling call. So just a general little layout here. We're going to talk now a little bit about the bypass damper. The purpose of the bypass damper is you have one constant volume of air coming out of a rooftop unit, and because you have zone dampers that are closing and limiting that volume of air coming through them, you have a buildup of air, a buildup of static in the duct, and you need to relieve that so you don't blow up a duct or you hear banging or anything like that. And so we have a bypass damper that measures the static pressure in the ductwork and then opens based on that and bypasses air to the return duct. Sizing of the bypass damper is very important. Ideally, how you want to size it is for the total CFM of the unit, the air handler or rooftop, minus the smallest zone CFM. So if you have all of your zones closed except for your smallest zone, then you would have that much air, the unit CFM minus the small zone CFM, bypassing through that damper. So that damper should be sized to handle that amount. This doesn't always happen, so a lot of people will say rule of thumb minimum of 75% of the unit CFM or rooftop CFM. It's a good guideline, but the best way to do it is to actually get the smallest zone CFM and take that difference. And then you want to select a maximum of around 1,500 feet per minute for velocity, just because a lot of times these bypass dampers won't be near the zones themselves, so you won't have a problem with noise, but you still don't want it too loud, any banging. So proper sizing of the bypass damper and location of the bypass damper is important in order to prevent short circuiting. If you have a oversized bypass damper, which is allowing too much air through the bypass damper, you don't have the best control of it. This is going to affect your supply air temperature. Say, for instance, if you're in heating mode and you're discharging 120-degree air, if you're bypassing a large quantity of that air, then that's going to go directly back to your unit and then sent back through the heat exchanger, and that temperature is actually going to increase your supply air temperature. So if your bypass is not sized properly or located properly, you could be short-circuiting and then either increasing your supply air temperature in heat mode or decreasing your supply air temperature in cooling mode, and that causes problems. You can start to heat, freeze, or overheat coils, and you can also dump or stratify air into the spaces, which is something you don't want to do. And another part of short cycling is properly mixing the bypass air with the return air, and we're going to look a little bit more into that on the next couple slides, but it's very important as well to prevent your supply air from getting too high or too low. VVT systems, like we mentioned before, one of the names was constant volume zoning. You can actually do a VFD application with a VVT system. It is very possible. The only issue you run into is if you have a VFD on an air source, you need it to have modulating heating and cooling. You need to be able to back that VFD down, but also back down that heating or cooling so you don't burn a coil or freeze a coil. And because of the size and the tonnages that are available, that we generally recommend for VVT, most air sources don't come standard with hydronic heat or cooling, or digital scroll compressors for modulating cooling or modulating gas. That's why it generally doesn't come up using a VFD, but it is possible. We say you can only do it with hydronic heating or cooling, but you can also do it with a digital scroll or any type of modulating cooling or heating. So it is possible. So for locations of the bypass, there's two that are shown here. If you look at the top one, we have a plenum return, and the bypass is just discharging air into the plenum, and that air gets to circulate back to the return, back up to the rooftop. And then on this one, we have a ducted return. One thing that is very important with these bypass dampers is not locating the bypass damper directly below the rooftop in between the supply and return. This is critical because you will definitely run into short circuiting where you are cycling 120 degree air back into the rooftop. It's not mixing properly with the return, and that's getting sent to your heat exchanger and just getting heated up even more. And then you're discharging 140 or 150 degree air to the zones, and that's going to stratify and maybe trip your high limit supply air temperature, and nothing good is going to come when you put them in that location. So we're going to discuss little rules to give you a little bit of guideline here. So for the plenum return application, you always want the bypass damper facing away from the return inlet. This is because it gives you, if you're shooting air out away from the return, it gives it more time to mix with the plenum air and then eventually get back into the return inlet, so you have better mix between it. One thing to note on the static pressure sensor location, a lot of times the sensor will be located on the zone controller, so you'd have to run your pneumatic tubing down into the duct. You want to go at least 5 duct diameters downstream of the bypass takeoff. If you don't, you're not going to have, you want to get it as far away from turbulent air as possible, so you want to get as far away from that inlet of the rooftop, away from the bypass damper itself, to get the best reading you can get. A lot of times this doesn't happen, but ideally you want to do at least 5 duct diameters downstream. And you have to make sure you're upstream of the zone dampers, because when those zone dampers close, you're not going to read a static. Your bypass isn't going to know what to do. So the other application where you can use your bypass damper is if you have a ducted return. Ideally you would like it far away from the inlet, but again, this isn't always possible with the space you have available. What we recommend for ducted returns is to be a minimum of 15 feet from the unit inlet. So you want to get it as far away from the outlet and inlet of this unit so that you're not short-circuiting. One other important thing, if you have a ducted return, is to have a return backdraft damper. You can possibly run into issues where when you are bypassing air through this unit, this bypass damper, if you don't have a backdraft damper, you can actually leak air out of your return diffusers. And that is not good, especially when you have 55 degree air coming out to your zones and coming out of your return dampers, your return registers, I'm sorry. It's not good for the temperature, and it's not good for pressurization of the building. So again, you want to put your static pressure tubing 5 duct diameters downstream. Again, this is all ideal. I know it doesn't happen in every case, but you need to try to strive for this if you want it to run properly. There are a lot of applications with VVT where it's the right application, it's just not, the bypass damper isn't sized right or not located right, and you run into big issues where you got temperature control problems, you got short cycling of the unit, and it is not good. So leaving air temperature protection is something that comes standard on carrier VVT controllers, and it is a safety logic built in for the VVT system. So what it does is it reads the leaving air temperature, and as more air bypasses, it actually stages the cooling and heating modes to prevent your supplier temperature from getting too low or too high. So just a general example would be, let's say you have 55 degree air discharge air set point, okay? If you're bypassing a lot of air, your discharge air might start to go below that 55 degrees. And you don't have modulating cooling, you don't have a chilled water coil that you can modulate down, but if you read that your supplier temperature gets down to 50 degrees, you would shut off your second stage of cooling to try to prevent it from going below that. And then if it continues to drop because you're short cycling so much air, you could actually shut off your first stage of cooling at 45 degrees. So it's a built-in limit or safety within the control logic. It will be helpful to protect the unit and make it run longer where you're not tripping on limits or you're not freezing coils. And the same works on heating too. You would just do it the reverse. So you shut off second stage heat when you're up to 130 degrees and then first stage heat when you're up at 140. So system mode selection, I guess, is just kind of a general overview of the sequence of VVT. The rooftop unit in a VVT system is completely controlled by the zones. So the zones decide when the unit goes into cooling or goes into heating. Most of the time it's set up where one unit can call for the zone to be on, or the rooftop unit to be on, I'm sorry, but you can set it up where maybe you need at least 2 zones to call before you can turn the rooftop unit on. It's all programmable of what you want to do. But the general sequence is each zone has its own set point and space temperature sensor. And whichever zone, there's a couple ways you can do it. You can do it where whichever zone is furthest away from set point would be the caller to the rooftop unit, or you could take an average of all the zones, and whenever that average is below set point enough, it will kick on, or above set point enough, it will kick on. But basically the thing to remember is that the zones themselves are controlling the rooftop. And once the zones call the rooftop to go on, then each zone will control its own damper based on what temperature it needs and what temperature it's reading from the rooftop unit. A general sequence that's built into most VVT systems is an all zones satisfy clear mode. So in order for a unit to switch from cooling to heating mode, you will need all of the zones that were calling for cooling originally to be satisfied. So if you have the unit going into cooling because 2 zones are calling for cooling, if one of those zones satisfies but the other is still not there yet, the unit will still run cooling until that other zone becomes satisfied, and then it can switch into heating. And generally another good thing to include in your sequence is a minimum heat and cool runtime. This prevents you from switching over from heating and cooling and actually fighting zones. You never want 2 zones to be fighting each other within the system. So if you limit at least a minimum runtime for the heating and cooling mode, you'll prevent fighting within the system. And just some general rules, we usually use 3 minutes for most HVAC equipment and then 5 minutes for heat pumps. So let's keep going here. Obviously with codes, we definitely need ventilation minimums. At least that's what's recommended through code. You're allowed to have a ventilation percentage set point for each zone damper. So if a zone is not calling for heating or cooling and the rooftop unit isn't providing hot or cold air, just ventilation air, you would have a set point where you can set your zone to a specific percentage, let's say 25% or 50% for your zone ventilation air. Obviously, this doesn't always happen because you don't always have neutral air coming from the rooftop unit, but when you do, you're allowed to put a set point in there. With codes, I'm not 100% sure and familiar with the codes, but I know you're generally supposed to have a minimum ventilation requirement. When you have this minimum ventilation requirement with a VVT system, a lot of times you run into issues. And the issues are when you have a zone that's calling for heat, but the rooftop unit is providing cooling. If you have a minimum percentage set on that zone damper of, say, 10 or 15%, you're actually providing cold air to a zone that's already cold and that needs heat. Obviously, the VVT system can't provide the right air to each system unless you have reheat on it. But if you don't set your minimums to 0, you could be potentially hurting the system when you have one zone damper that's calling for heating, but the rest of the zone dampers are calling for cooling. If you have a minimum of 10 or 15%, that heating zone is actually going to get colder and colder because you're providing 55 or whatever your supplier temperature set point air is to that zone. So ideally, if you can set your minimum zone damper positions to 0, you will have the best control you can get with a VVT system. Again, it's not always possible. It's something that we like to shoot for. So, CO2 and Demand control ventilation is definitely possible with VAV and VVT. One thing that is a common misconception here with any of these systems is you cannot have a return air CO2 sensor. Ideally, that would be the best case because it would be cheapest, but in order to do this properly, you need to have a local CO2 sensor in each zone. And if you think about it, let's say you have just one return air CO2 sensor. If you have all of the people in your building normally in all of their offices, your return air should be normal. But if you take all those people and put them in one zone, that zone is going to be calling for CO2, or I'm sorry, for outdoor air because it has high CO2 levels, but the unit's not going to know because the return air the return air CO2 reading is going to be the same because you have the same number of people. There's not more people there than there were. So even though one zone requires outdoor air, the unit's not going to know that it needs it. So you need CO2 sensors in each zone locally. A wall-mounted CO2 sensor can cover up to 5,000 square feet of open space. When you have CO2 on a VVT system, your first stage in response to that CO2 sensor should just be opening the zone damper. Let's say you have a bunch of people in a room and the temperature set point is satisfied, so the zone damper is at a minimum, but your CO2 levels are increasing. Even though you have, say, 55-degree air coming out of that zone, you should still open first and see if you can satisfy that CO2 set point based on the minimum outdoor air position of the economizer or outdoor air damper on the unit first before you start opening that economizer damper or outdoor air damper. So that should be your first stage, and then if you can't satisfy that way, you should open up your outdoor air damper more to get more ventilation air. For more information on DCV, you can go to ASHRAE's website. There's a bunch of codes and descriptions of the best way to run DCV, but it's pretty simple, very applicable for VVT systems. You just need local CO2 sensors. So we talked a little bit about supplemental heat. Supplemental heat is a nice feature for any zoning. It's not always possible, but it is a nice feature to have. All of Carrier's VVT controllers come standard, able to use any of the supplemental heat types seen on this list. So you can do 2-position hot water. You can do 1 to 3 stages of electric heat. You can do modulating hot water. You can do modulating electric heat. Then you can actually do a combination of both. Let's say you had 1 stage of baseboard and 2 stages of ducted heat. You could actually say your baseboard is your first stage of reheat, and then you would actually stage your stage your ducted heat coil after that for your second and third stages. So supplemental heat is very important if you are serving 2 exposures, 2 exterior exposures, or if you're mixing interior and exterior zones on a VVT system. And like we said before, if you have one exposure exposed to sun and the other isn't, that sun exposure is going to be calling for cooling, but the other one could possibly need heating. And if you have supplemental heat, you can satisfy that. So it's a nice feature to have. You always want to make sure that the supplemental heat is your first stage of heat. So if you have a zone that calls for heating, it will enable its supplemental heat first, and then if you still can't satisfy your heat call, you would switch to your rooftop or air source as the heat mode. This is so that you don't affect other zones negatively when you could be using your own supplemental heat. And then standard things apply, like lockout based on outdoor air. Obviously, you don't want to be heating when it's 85 degrees outside. That's something that's just standard in control sequencing. One thing to note that gets overlooked a lot is in order to get proper dispersion of air out of an overhead ceiling diffuser, you do not want discharge air above 90 degrees. Above 90 degrees, and I believe this is an ASHRAE code, technically the air will start to stratify and you will not get proper dispersion. So when you're sizing your reheat coils, you want to size them for discharging 90 degree supply air out of the diffusers if you have overhead diffusers. Fan powered boxes are generally seen with VAV type systems. However, for VVT, you can use fan powered systems. You don't really see them because VVT systems are a lot smaller, but the application is exactly the same for VAV systems as VVT. You can use them, for instance, if it's a series fan powered, if you need that extra that extra push down the ductwork in order to overcome that extra static pressure. Works the same. You just downsize your air handler supply fan and then use your series fan powered box. Or you can use parallel fans and run the first stage of zone heat as the return air from the plenum. All of Carrier's controllers come standard with an output for enabling a fan. So if you ever have a VVT system with a requirement for fans, something that's standard on a Carrier VVT controller. General control systems for VVT. VVT is generally DDC based, and with most DDC systems nowadays, they are internet accessible. So you're able to view and modify data, send email alarms, perform diagnostics, and you don't require dedicated PCs anymore where you just have one PC for the whole system. You can broadcast these on the internet, get them on your smartphone, on your iPad or tablet, or any other computer connected to the internet. So this is a great feature to have with a DDC system so that you can remotely look at what's going on, see what the temperatures are, and diagnose what's happening. You can get alarms. Very nice feature, something you should always try to include with a VVT or any DDC control system. Air balancing. Air balancing is very important for these VVT systems. Unfortunately, it doesn't always happen, and there's a few guidelines that we have on this slide and the next of what type of air balancing we need to do, at least minimum-wise, so that we can get the proper control. But one thing I'd like to stress, the most important thing when it comes to air balancing is making sure you get an air balancer and someone who knows the control system on site at the same time so that they can coordinate how the control system works and how the air balancing is supposed to be set up. Personally, I've commissioned controls on many job sites where I haven't even seen an air balancer, and the air balancer never even shows up. And we can't control the system the best we can without an air balancer to help us. If you don't have the system balanced properly, you might not get the proper CFM out of zones, and some zones will always be calling because they don't have the proper airflow coming out of them. You can have a bypass damper that has a static pressure set point that is not the total static pressure that's in the duct, or that's not supposed to be maintaining, and you could be bypassing too much air. There's a number of situations that you can run into without having an air balancer here. And I like to stress having something set up where the controls contractor or someone who knows the control system out there with the air balancer so that they can coordinate and control properly. So just a few outlines of what you would want to go through when you're doing air balancing the system. This next slide has a little bit of continuation with the outdoor air. I don't want to go too in detail with it, but it's important to make sure that you set up air balancing and that you have someone there who knows the system as well. So just real quick on what Carrier can offer for its DDC VVT system. We have a standard application controller called the RTU-Open controller. You can get these factory installed in any Carrier rooftop unit, or you can field install them in any rooftop unit. The controller runs through the thermostat terminal of the rooftop, so it calls for heating and cooling and fan the same way a regular thermostat does, but this has all of the VVT logic built into it, pre-programmed. It just needs to be configured. It can control 2 stages heat-cool, economizer. It can actually do the 2-stage or VFD fan control now, and these are actually able to connect to other BAS systems, Modbus, BACnet, LAN. It is a native BACnet controller, but this would be the controller that we would include on any Carrier VVT system. And one of the big proponents of why is because it supports what Carrier calls airside linkage. And airside linkage is Carrier's pre-canned program that allows this controller to communicate with the VVT zone controllers to read their space temperatures, their set points, their damper positions, all it needs to know in order to respond properly. That's all pre-programmed from Carrier. And Carrier actually bought out Parker when Parker first developed VVT, so they've been doing this for 20, 30 years now. All of that algorithm is just built in, ready to go, ready to be programmed. So I'm sorry, configured. And then the actual zone controllers that would go with that RTU-Open controller, we have the VVT zone controller and the VVT bypass controller. as you can see, the actuators are actually built into the controller. So this slaps right on the shaft of the damper, and then all of the control logic is built into here. You can see for the bypass controller, it actually has the static pressure sensor built into it here. You just connect your pitot tubes to the static pressure tip. But all these controllers have those outputs for electric heat or modulating heat that we talked about before, 1 to 3 stages of electric heat on a hot water, modulating electric. It can do optional fan. If you have a fan powered box, you can slave the high torque actuator off of them. Everything on these controllers is pre-built from the factory. You just need to tell it what it needs to do. So you just go through a question answer of saying, hey, you have hot water reheat that's modulating. You are a size 1600 zone damper, something like that. And it is all set up to run, all set up to communicate with the RTU-Open controller for the proper VVT system. So that's what Carrier can offer. Real quick, we're just going to go over, I guess, a summary of what the do's and don'ts for VVT systems, and then I'm going to show you a VVT system that we put in, and then we're going to go over some questions. So, some don'ts right off the bat. You do not want to do a VVT system over 20 tons. Usually, applications that size would require a cooling all the time load, so you'd want to go with VAV. You never want to reduce the quantity of air handlers or rooftops to do zoning. So if you size a building and you decide, hey, I need to do 3 rooftop units at 10 zones apiece, you do not want to take one of those rooftop units out, put in a 20-ton and do zoning. You want to use VVT systems when you already have this right-sized rooftop, and then you want better comfort, better control with zoning. Just another general rule. I hope you guys hear this more and more. You don't want to oversize anything. Everything, most of all the equipment that's out there that's not new is already oversized. Oversizing does not help out unless you can do some sort of modulation, which you don't see a lot, and even still, it's not the best. You should be designing for what the loads that you are calculating. When you oversize, you overcool, you dump, you stratify. You don't want to oversize any type of equipment. Another don't is mixing interior and exterior zones. I know the conceptual layout we showed you did do this, and that was okay because we had supplemental heat. But if you do VVT zoning where you have a west exposure, an east exposure, and a central exposure, and you don't have any supplemental heat, you're going to be fighting the whole time. The whole day you're going to be calling for either cooling or heating when one zone is only requiring heating and the other zone's calling for cooling. So you want to make sure that your zones are similar type of loads so that you can control properly. Another don't we talked about was with the bypass damper. You don't want to install it too close to the return inlet because you can get short cycling. You also don't want it to be too close to plenum return grills because you want that air from the return and the bypass to mix as best it can before it gets back to the rooftop unit. The better the mixed air of your return, the better control you're going to have, the better supply or discharge air you're going to get. One do that we want to stress again is specifying the complete scope of air balancing. You want to tell your air balancer that they need to do all of those requirements that we listed on the previous slides, and you want to make sure that they're out there when the controls contractor's out there so they can coordinate the proper control. And then the most common problem that we see, that we don't like to see, is specifying minimum damper positions for ventilation. Again, I'm not 100% sure of the code. There could be some ventilation code requirements, but when you have minimum positions set, you're going to be cooling spaces that require heat or heating spaces that require cool, and then your system's just going to be fighting itself. You want to try to get them to go fully closed in order to properly control a VVT system. So, real quick before I get to your questions, I'm just going to show you one of Carrier's VVT systems that we put in. The system is called iView, and it is a web-based system where I think there's 7 floors of control that we provided, and I I think there's about 14 zones of VVT here. So this is actually an application where we did VVT with a VFD because we had chilled water and hot water control. So this is a Carrier iView web interface. This is kind of just the general look of it. So if you can see here, we have 7 floor plan graphics of the 7 floors that we're controlling. You see these top 4 floors are the ones that are zoned, and they actually have little thermodynamic bubbles. These green and yellow bubbles are actually the zone temperatures for each one, and you can click on these and they will take you directly there. But we're going to look really quick at the 5th floor, which has 1, 2, 3, 4, 5, 6, 7 zones. So you can see that these zones are actually displaying the temperatures, live temperatures of the space sensors of each of them. And then you can see what the air handler is actually doing. You can click on any of these bubbles. You've got an outdoor air temperature. So I'm going to click on this air handler for air handler 5 here real quick. It will actually take you to a live animated graphic of what that air handler is doing. You can see that the supply fan is actually moving. I'm not sure if it's showing up for you guys, but that wheel is actually spinning. You can see I've got a VFD on here that I'm maintaining a duct static at, and then I've got my supply air and my set point. This is what's called a linkage space temperature set point. And what it's doing is taking the average of the space temperatures of all of the zones that are on this system, averaging them, and then telling this zone, this unit, hey, this is what your space temperature is. And then it's also taking the average of the set points down here, and then it's telling it to the air handler, so it runs off of that. So if we want to go to a specific zone, let's say we go to southeast south center zone, we can see that our space temperature set points are 70 and 74. Space temperature is 73.7, so we are satisfied. And this zone damper is at its minimum position. Again, they had minimum code requirements they needed to meet, so they did not let us enter in 0 for the minimum position, so we're at about 10% for our minimum position, but ideally we would like to go to 0 to properly control the system here. So this is just an example of something that we can do with Carrier. I mean, we can do full control of any system too. I mean, there's actually controlling boilers on this system as well. It's got 2 boilers and boiler pumps, but just a little overview of how a VVT DDC system should look here. All the different views and everything. So other than that, that pretty much concludes the webinar here. I'm going to look real quick at the questions box to see what kind of questions we have, and then should be wrapping up. So first question here. What are some energy efficiency opportunities in older example of these systems? It's a good question. I mean, VVT, the point of VVT originally was not to save energy. It was more to provide better comfort, and that's because you technically aren't able to modulate the fan, and the fan's a big energy killer. If you could retrofit an existing system where you have the ability to modulate cooling and modulate heating, then you could get into some sort of energy savings where you are modulating with a VFD and doing VVT with the VFD. On that previous example that we just looked at on that system, those four air handlers that we were controlling were actually multi-zone systems that we retrofitted with with VVT with VFDs. So we were able to save energy where we're modulating the fan down and then also modulating cooling and heat. So that really is the most that you're going to run into. For energy savings, I mean, again, with VVT, you're not modulating the fan. That's the biggest killer. So I don't really see a lot of other energy savings that you could get. Other question we have is, when I'm standing on the roof looking at the RTU, how can I tell whether it is a VVT system? That would depend a lot on what type of control, what type of VVT system it has. When you're looking at a rooftop unit, if you can see a DDC controller within it, that would be my first guess that you would have a VVT system. Another thing to look for would be if you could get into the ductwork area, if you could see a bypass damper, would be another sign. or if you see any type of zone controller or sensor in the space that looks like it's not a standard thermostat, that would be another thing that's telling you, hey, you might have a VVT system here. Or if you can trace, I guess, if you can trace the wires to the thermostat terminal on the rooftop unit to multiple locations, if it's going to a relay board that's going to different zones, that would be something else that would indicate you have VVT. But I guess there's not just one thing you can look at and say, hey, I've got a VVT system just based off of a rooftop unit without actually getting inside of it. So sorry, I couldn't help more on that one. The slides will be available. I think we're going to post them on Dropbox, but I could talk to Ryan about posting them on the website. But the webinar is being recorded and will be posted on TEC's website so that you can reference it if you have any questions or want to look at anything that we went over. So other than that, if you guys do not have any other questions, thank you very much for attending. VVT systems are a great way to control HVAC, especially for office buildings. So something that if you have any questions, you can contact me. My email address is listed right here, sal.stangaroni@tecmungo.com. Shoot me an email with any questions you have. You should be able to reference the webinar once it gets posted, but other than that, thank you again for coming. Appreciate it.